Welcome to Hovercraft Physics and Chemistry. In this video, we will consider an energy problem involving a bungee jumper. To solve this problem, we will model the bungee cord as an ideal spring and use the concept of elastic potential energy to solve the problem. Let's jump right in. Let's take a look at some of the details of the problem. First, let's consider the starting point in the problem. The bungee jumper, with a mass of 85 kilograms, stands at a height of 75 meters. The bungee cord itself is 10 meters long. If we imagine what happens, the bungee jumper would jump, they would fall a certain distance, and then the bungee cord is going to become stretched, and the problem says that the bungee jumper will be brought to rest at a height of 5 meters above the water. We would like to know what the bungee jumper's speed is just before the cord begins to stretch. That would be at this point. And we'd also like to model the bungee cord as an ideal spring. So we're talking about elastic potential energy or spring potential energy. They're basically the same thing. The formula for elastic potential energy has a spring constant in it, and that basically describes the stiffness of the spring. In this case, we could think of it as the stretchiness of the bungee cord. Spring constant is measured in newtons per meter. It tells you how many newtons of force you get per meter of stretch. Then we'll consider a case where some energy dissipates. So as this bungee jumper falls, there would be frictional effects, air resistance, stretching of the bungee cord, and all of those things could generate some thermal energy. I like to dump that under a term called dissipated energy. Dissipated energy is the thermal energy increased caused by frictional effects, stretching, warping, and vibrations. In the last part of this problem, we'll assume 3,675 joules of energy is dissipated through the course of the jump. Because of that, we wouldn't expect the bungee jumper to snap back to the original height. Using this dissipated energy total, we'll determine just how high the bungee jumper will reach when she rebounds back. In the first part of this problem, we're going to try to find the speed of the bungee jumper when she reaches this point. The problem told us that the length of the cord was 10 meters. That means the bungee jumper would be at a height of 65 meters at that point. We're going to assume that the bungee cord length and the height are equal. That wouldn't be exactly true, but it'll give us a good estimate of the quantities that we're trying to solve for. So we'll call this height 65 meters. In energy problems, it's always appropriate to pick a height 0. You could use the bungee jumper's lowest height as height 0, but for our purposes, just to keep things simple, we're going to go ahead and call the water level here height 0. One other thing I'd like to know is just how stretched the bungee cord becomes. At this point, it's unstretched at its 10 meters length. Once the bungee jumper reaches this height, the cord begins to stretch and we start to have energy stored in the stretched bungee cord. The equation for elastic potential energy or spring energy includes this stretch amount. If the bungee jumper is at height 65 meters when the cord is unstretched and a height of 5 meters when the cord reaches its maximum stretch, the stretch length here is 60 meters. In the spring equation, that's usually called x. I also like to use energy pie charts to organize my thinking on this sort of problem. So let's put an energy pie chart here. This is really going to dictate how much total energy we have in the system. Let's also consider the energy pie chart when the bungee jumper reaches the unstretched length, because we do want to find the speed of the bungee jumper at that point. We'll also look at the energy pie chart when the bungee jumper is 5 meters above the water. For the starting position of the bungee jumper, the entire energy pie chart is gravitational potential energy. E subscript G. That's because the bungee jumper isn't moving and the bungee cord is not stretched yet. When the bungee jumper falls to this height, 65 meters, there will be less gravitational potential energy because the bungee jumper is closer to the ground. At this point, the bungee jumper will be moving as well, so there will be some kinetic energy to include in the energy pie chart. It might look like this. With the remainder of the pie, gravitational potential energy. At this point, the bungee cord begins to stretch, so we'll see a third type of energy come into the energy pie chart. When an elastic object, like a bungee cord, becomes stretched, it stores energy. That's called spring potential energy or elastic potential energy. As the bungee jumper falls to the final height of 5 meters, that elastic potential energy is getting bigger and bigger. All the while, the kinetic energy is becoming less and less. The stretched bungee cord will slow down the bungee jumper until she comes to rest. There's a lot of elastic potential energy at that point, and a little bit of gravitational potential energy. Maybe that'll look like this. I'll include a small sliver of gravitational potential energy, and quite a bit of elastic potential energy. I'll use the symbol E subscript EL for elastic potential energy, but it's really the same as spring potential energy if you prefer E subscript S. Now let's get into some problem solving. The first question asks for the speed of the bungee jumper when she reaches this height, the point where the bungee cord begins to stretch. I'm going to compare the energy total here and here in order to solve that problem. Let's go ahead and call this position 1, this position 2, and this position 3. We're assuming for the first half of the jump here that energy is conserved and there is no dissipated energy. So we can assume whatever the energy total is here should equal the energy total here. So for position 1, I have all gravitational potential energy equaling some kinetic energy at point 2 plus a large amount of gravitational potential energy that remains. The formula for gravitational potential energy is mgh, mass times g times the height of the object. I'm going to put a subscript 1 here to talk about the height at position 1. On the other side of the equation, the formula for kinetic energy is 1/2 mv squared. I'm going to put a subscript 2 here just to make sure that we're talking about the speed at position 2. And there's still quite a bit of gravitational potential energy, mgh. And I'll use subscript 2 here to denote that that's the height at position 2. If this was the only problem we were solving, I would probably cancel the mass out of each term. But this problem also involves elastic potential energy, and the formula for elastic potential energy does not include mass. It includes the spring constant, as well as the amount of extension or compression of that elastic object. The third problem also includes an energy amount in joules. If I want to know any of these energy amounts in joules, I do need to include the mass of the object. In my previous problems, I did algebra first to solve for the unknown. In this case, our unknown is going to be the velocity at position 2. This time around, I'm going to go ahead and plug in numbers first and then solve for my unknown. So on the left-hand side of the equation, I'm going to plug in the mass of the bungee jumper, 85 kilograms, times the value of g, times the height at position 1. That's 75 meters. I'll shift this over so that we know that this whole side of the equation represents mgh, plugging it on the right-hand side of the equation. 1/2 times the mass of the bungee jumper, 85 kilograms, times our unknown velocity squared, plus the gravitational potential energy at that point. That's the mass of the bungee jumper, times the value of g, times the new height at position 2. That's only 65 meters. I'll go ahead and punch those values into my calculator and report each value in joules. The energy total on the left-hand side of the equation is 62,475 joules of energy. Remember, that's our starting energy total, and we assume that that energy total is conserved throughout the first half of this problem. I'll go ahead and take 1/2 times 85. That's 42.5 kilograms times our unknown speed, v2 squared. The rest of this is the gravitational potential energy total at position 2 at a slightly lower height, 65 meters instead of 75 meters. That total is 54,145 joules. I'm not rounding any of these numbers for significant figures just yet. Again, I want to solve for V2, so I'm going to subtract 54,145 joules from both sides of the equation. This will subtract to 0, and 62,475 joules minus 54,145 joules is 8,330 joules. That will equal 42.5 kilograms times the unknown speed squared. Now we need to divide through by 42.5 kilograms. That will cancel. And then taking the square root will get us our answer. And our answer, reported with 3 significant figures, is 14.0 meters per second. You can go through and prove that this does actually cancel out to meters per second. It takes a little bit of time because joules is based on the unit Newton meter, and newtons is based on the unit kilogram meters per second squared. If you work out all the cancellation, you do in fact end up with units of meters per second, but we expect that because we're solving for a velocity. So that's our answer to the first question, the speed of the bungee jumper right before the cord begins to stretch. The second question asked, what is the effective spring constant of the bungee cord? I'll present the solution to that problem in the next video in the playlist. If you have any questions about this video, please post them in the comments below. Thanks for watching.